Among all the worlds we have discovered, orbiting distant stars, one holds a distinction that seems almost impossible to believe at first hearing. This planet, known to astronomers as TRES 2b, absorbs nearly all the light that reaches its thick, superheated atmosphere. When researchers first analyzed the data from this distant gas giant, they found something that challenged their expectations about what planets can be. This world is darker than coal, darker than charcoal, darker than the blackest substances we encounter in everyday life on Earth. The discovery emerged from careful observations made by the Kepler Space Telescope, which spent years watching stars for tiny changes in their brightness. Among the thousands of worlds Kepler helped study, TRES 2b stood out for a reason nobody had anticipated when the mission began. This planet orbits a star roughly 750 light-years away from us, in the direction of the constellation Draco, the Dragon. The light we receive from that distant star tonight actually left its surface around the year 1270, traveling through empty space ever since. You're listening to The Drowsy Astronaut, and tonight we are spending time with the darkest planet ever found beyond our solar system. This will be a slow, unhurried journey through everything we know about this strange and remarkable world, with no rush and no pressure. If you are joining from somewhere around the world tonight, feel free to share where you are listening from in the comments below. And if you enjoy this kind of calm exploration of the cosmos, a like or subscribe helps others find their way here too. But for now, just get comfortable, and whenever you're ready, we'll begin. TRES 2b is dark, but not in a small or subtle way that required sensitive instruments to barely detect it against the brightness of other worlds. This world reflects less than 1% of the starlight that reaches it, absorbing nearly every photon that arrives from its nearby sun. To understand how remarkable this is, we need to consider what reflection means and how most objects in the universe interact with light. When light strikes a surface, some of that light bounces back toward where it came from, and we call this reflected light. The amount of light an object reflects compared to the amount it receives is called its reflectivity, or sometimes its albedo, a simple ratio scientists use. An object with high reflectivity bounces back much of the light that reaches it, appearing bright to any observer looking in its direction. An object with low reflectivity absorbs most of the incoming light, appearing dark because little light returns to waiting eyes or instruments. TRES 2b has one of the lowest reflectivities ever measured for any large object in the known universe. Fresh snow on a winter morning reflects about 80 to 90% of the sunlight that falls upon its surface. This is why snow appears so brilliantly white and can even cause temporary blindness on very bright days without protective eyewear. The surface of our moon, which appears silvery white in the night sky, actually reflects only about 12% of incoming sunlight. Earth as a whole reflects approximately 30% of the light it receives from the sun, thanks largely to clouds and ice sheets. These numbers help establish a scale for understanding just how dark TRES 2b truly is compared to familiar objects around us. A freshly paved asphalt road, the dark surface we drive on every day, reflects roughly 4% of the light hitting it. A lump of coal, the substance we often use as a reference for darkness, typically reflects between 3 and 4% of incoming light. TRES 2b reflects less than 1%, making it darker than both coal and asphalt, by a significant margin. Consider holding a piece of coal in your hand on a sunny afternoon, noticing how dark it appears against the brightness around it. That coal is still reflecting enough light for your eyes to see its surface texture, its contours, its slight variations in shade. A surface as dark as TRES 2b would reflect so little light that discerning any surface detail would become nearly impossible under similar conditions. The darkness is not merely deep, but approaches something like visual absence, a place where light goes and does not return. Scientists have created some of the darkest materials on Earth in laboratory conditions. Substances designed specifically to absorb as much light as possible. One famous example is a material called vantablack, made from carbon nanotubes arranged in a way that traps light within tiny spaces. Even vantablack, one of the darkest artificial substances ever created, reflects about 0.5% of incoming light under most conditions. TRES 2b approaches this level of darkness naturally, without any engineered structures, across an entire planetary surface the size of Jupiter. The measurement of this extreme darkness came from a specific technique astronomers use to study planets they cannot see directly with any telescope. As TRES 2b orbits its star, the total light we receive from that distant system changes slightly depending on where the planet is. When the planet is beside the star from our point of view, we receive light from both the star and the planet's illuminated face. When the planet passes behind the star, we receive only starlight, and the difference tells us how much light the planet was contributing. This difference turned out to be remarkably small for TRES 2b, smaller than for any other planet measured using similar techniques. The planet was contributing almost nothing to the total light from the system, even when its illuminated day side faced toward Earth. Researchers checked their calculations multiple times, looking for errors or overlooked factors that might explain the unusually low readings. The numbers held steady with each analysis, confirming that this world truly absorbs almost all the light reaching it. The darkness raises an immediate question that does not yet have a complete answer. And that question is simply, why? What causes a planet to become so extraordinarily dark when most planets and moons we know reflect meaningful amounts of light? The atmosphere of TRES 2b likely plays a central role, though the precise mechanisms remain subjects of ongoing research and scientific discussion. This is a hot Jupiter, a type of gas giant that orbits extremely close to its star, and that proximity creates unusual conditions. At such close range to its star, TRES 2b experiences temperatures that would be difficult to imagine from our comfortable vantage point on Earth. The day side of this planet reaches approximately 1800 Kelvin, which translates to roughly 1500 degrees Celsius, or about 2700 Fahrenheit. At these extreme temperatures, many chemical compounds that might form reflective clouds on cooler planets simply cannot exist as solid particles. Everything remains gaseous, creating an atmosphere with nothing to bounce light back toward the waiting darkness of space. Some researchers believe that gaseous sodium and potassium in the atmosphere may contribute to the extreme light absorption this planet demonstrates. Both of these elements, when heated to such temperatures and existing as gases, absorb visible light very efficiently across wide ranges of wavelengths. Another candidate is titanium oxide, a compound that appears dark and absorbs light strongly when present in hot atmospheric conditions. The combination of these absorbing chemicals with the complete absence of reflective cloud layers, could explain much of what we observe. The absence of clouds is itself a consequence of the extreme heat, creating a kind of feedback where conditions that make the planet hot also make it dark. On Jupiter, the gas giant we know best in our own solar system, the visible surface consists of colorful bands of clouds at different altitudes. Ammonia ice crystals form bright white zones, while other compounds create the tan and rust-colored belts that give Jupiter its distinctive banded appearance. These clouds reflect sunlight back into space, making Jupiter a relatively bright object, despite being so far from the Sun. TRES 2b has no such clouds because nothing can condense into solid or liquid particles at the temperatures its atmosphere maintains. The entire visible atmosphere remains a gaseous soup of hydrogen, helium, and trace amounts of light-absorbing chemicals floating in transparent mixture. Without cloud particles to scatter incoming starlight back into space, the light simply penetrates into the atmosphere and gets absorbed along the way. Each photon that enters eventually transfers its energy to the surrounding gas molecules, becoming heat rather than remaining as light. The depth of this darkness would make TRES 2b an unusual sight if we could somehow transport ourselves across the 750 light-years separating us. Approaching from a distance, the planet would be difficult to see against the black backdrop of space between the stars. Only the slight occultation of more distant stars as the planet moved in front of them might reveal its presence to watching eyes. The darkness would seem almost like a hole in space, a region where light simply stops existing and nothing returns. Yet, as we will explore later in our journey together, this dark world is not entirely invisible despite its remarkable light-absorbing properties. The extreme temperatures that prevent cloud formation also cause the planet to glow with its own faint light, a dim, reddish luminescence. This glow does not come from reflection, but from the planet itself, from heat energy being radiated outward into the coldness of space. The same forces that make TRES 2b the darkest planet also make it a source of its own subtle illumination. For now, we remain with the darkness itself, letting the scale of this light absorption settle into understanding without rushing toward other aspects. A world darker than coal floating in the void of space, orbiting a star much like our own Sun, 750 light-years away. The coal comparison works well because coal is something many of us have held, have seen, have recognized as a standard for darkness. Knowing that an entire planet surpasses even coal in its ability to swallow light opens a quiet sense of how varied the universe can be. The constellation Draco winds across the northern sky, an ancient star pattern that different cultures have seen as a dragon or a serpent. Within this constellation, too faint to see with unaided eyes, but detectable with telescopes, lies the star that TRES 2b calls home. That star shines with yellow-white light, much like our own Sun, appearing thoroughly ordinary in most respects, unremarkable among the billions of stars. Only the presence of this extraordinary dark planet gives that particular star any special significance in the catalogues astronomers maintain. 750 light-years means that the light reaching our telescopes tonight has been traveling since medieval times on Earth, crossing emptiness for centuries. During all those years of travel, that light carried no information about the dark planet, because planets do not emit the kind of light that travels so far. What we detect is the star's light, and how it changes as the planet moves, a subtle dance of brightness variations revealed through patient observation. The darkness we have measured is real, confirmed by multiple observations, and it waits there still, around that distant yellow star. As this dark world continues its endless orbit, absorbing starlight and radiating heat into space, we will continue our exploration of its nature. The glow that emerges from this darkness forms a central paradox of TRES 2b, and understanding that paradox comes next in our journey together. A planet so dark it swallows nearly all incoming light, yet visible through its own thermal emission, glowing like a cooling ember against the night. The extreme heat that prevents cloud formation and enables light absorption also drives the planet's temperature high enough to produce visible radiation. At approximately 1800 Kelvin, objects glow with a dim reddish color, similar to iron heated in a forge, until it just begins to show color. This is not reflected light returning from the surface, but light created by the planet itself, generated by the thermal motion of its constituent matter. Every object above absolute zero emits some electromagnetic radiation, and at high enough temperatures, that radiation includes visible light. The physics behind this phenomenon is something scientists call black body radiation, though the name can be somewhat misleading in everyday language. A black body is an idealized object that absorbs all incoming radiation perfectly, reflecting nothing at all, which is close to what TRES 2b actually does. Such objects then emit radiation based purely on their temperature, with hotter objects emitting more energetic radiation that shifts toward bluer colors. At 1800 Kelvin, the peak emission lies in the infrared range, but enough energy spills into the red end of visible light to create a faint glow. This means TRES 2b would not appear completely invisible, even to human eyes adapted to the darkness of space around it. Instead, the planet would show as a dim red presence, like the last coals of a fire that has burned down to embers hours ago. The glow would be subtle, easy to miss against brighter objects, but present nonetheless as a soft, reddish warmth against the cold black of space. The darker the planet is at absorbing incoming light, the more efficiently it behaves as a thermal radiator, connecting these two properties intimately. The warmth of the day side, heated constantly by the nearby star, produces this glow across much of the hemisphere facing the stellar furnace. Even the night side of the planet, forever turned away from its star, likely glows to some degree because heat circulates through the atmosphere. Winds carry thermal energy from the scorched day side around to the permanent darkness of the night side, evening out temperatures somewhat. The entire planet probably radiates in the red and infrared, a dark sphere wrapped in its own faint thermal luminescence. The color of this glow tells us something about the temperature directly, because color and temperature are linked through well-understood physics. Objects at around 1000 Kelvin glow a dull red, barely visible, like the first hint of color in heating metal. By 1800 Kelvin, the glow has shifted toward a brighter orange-red, more visible but still quite dim compared to the brilliance of the nearby star. This temperature also helps explain the atmospheric chemistry, because different compounds become stable or unstable at different thermal ranges. At temperatures below about 1000 Kelvin, clouds of silicate particles can form in gas giant atmospheres, creating hazy layers that reflect some light. Above this threshold, silicates remain gaseous, and the atmosphere becomes more transparent to incoming radiation, allowing light to penetrate deeper before absorption. TRES 2b sits well above this threshold, ensuring that no silicate clouds form to brighten its otherwise impossibly dark exterior. The heat that makes it glow also makes it dark, two consequences of the same extreme proximity to its parent star. The glow we are discussing is not bright enough to illuminate anything the way a lamp illuminates a room or a fire illuminates faces gathered around it. Instead, it represents the minimum radiation that any object at this temperature must emit according to the fundamental laws governing matter and energy. If you could somehow stand near this planet without being destroyed by the extreme environment, you might perceive the glow as a barely visible warmth. The darkness and the warmth would coexist, the planet absorbing starlight while simultaneously creating its own faint light from within. Scientists detected this glow by measuring the infrared radiation coming from the TRES 2b system at different points in the planet's orbit. When the planet's day side faces toward Earth, the total infrared radiation we receive from the system increases measurably beyond the star's contribution alone. When the planet passes behind the star and its day side is hidden from our view, the infrared signal drops accordingly. These variations allowed researchers to estimate the day side temperature with reasonable confidence, despite never seeing the planet directly in any image. The temperature of 1800 Kelvin makes TRES 2b one of the hotter known exoplanets, though not the hottest ever discovered in our expanding catalogue. Some hot Jupiters orbit even closer to their stars and reach temperatures of 2000 or even 3000 Kelvin at their day sides. At such extreme temperatures, the glow would shift from red toward orange and eventually yellow, becoming brighter and more visible to human perception. TRES 2b sits in a middle range, hot enough to glow visibly, but not so hot that the glow becomes intense. The connection between darkness and glow creates a satisfying consistency in the physics describing this distant world, without any contradiction or mystery remaining. The planet is dark because it absorbs incoming light, rather than reflecting it, behaving like a nearly perfect absorber in the visible spectrum. The planet glows because it is hot enough to emit its own thermal radiation, behaving like a source of light, rather than a reflector. Both properties stem from the same underlying situation: a gas giant parked extremely close to a sun-like star, roasting in stellar radiation. Imagine the visual experience of approaching this world from a great distance, moving closer and closer across the emptiness between stars. At first, you would see only the star itself, a yellow-white point of light growing slowly brighter as the distance decreased with each passing day. The planet would remain invisible against the stars, too dark to distinguish from the black backdrop of space, absorbing the trace amounts of light. Only when you drew close enough for your eyes to detect the faint thermal glow would the planet begin to reveal itself. The first hint might be a slight reddish warmth in a location where no warmth should exist, an unexpected presence near the brilliance of the star. As you approached further, the shape would resolve, a dark sphere with a dim, ember-like glow emanating from its day side, facing the stellar furnace. The night side would remain darker still, though perhaps showing a faint warmth from the heat carried around by atmospheric winds to that permanent shadow. The whole planet would seem like a hot coal floating in space, dark enough to disappear, yet warm enough to faintly shine. This dual nature, dark yet glowing, defines TRES 2b more than any single characteristic, taken alone, ever could. The darkness is remarkable, record-breaking, a property that sets this planet apart from every other large body ever measured by scientific instruments. The glow is equally important, providing the visibility that allows study and the temperature information that helps explain the darkness itself. Together, they create a world that is simultaneously invisible and visible, absorbing and emitting, dark and luminous. The physics at work here applies to all objects in the universe at all temperatures, not just to extreme examples like this distant planet. Your own body emits infrared radiation constantly, a glow too long in wavelength for your eyes to detect, but visible to infrared cameras. A cup of hot coffee glows in the infrared more brightly than the table beneath it, because its temperature is higher. Everything above absolute zero radiates, and only the temperature determines what wavelengths that radiation occupies and whether we can see it. TRES 2b simply pushes this universal behavior into an extreme regime where the emitted radiation enters the visible spectrum we can perceive. The planet has become hot enough through stellar heating that its thermal glow includes wavelengths of red light our eyes could potentially detect. At the same time, its atmospheric composition has made it dark enough that virtually no reflected starlight competes with this thermal signature. The glow stands alone, unaccompanied by any reflection, the sole visible property of an otherwise hidden world. As we continue our exploration of this remarkable planet, we will turn our attention next to the star at the center of its system. That star provides all the energy that heats TRES 2b to such extreme temperatures, driving the conditions that create both its darkness and its glow. Understanding the star helps us understand the planet, and the relationship between the two reveals much about how systems like this form and evolve. The star waits 750 light-years away, visible as a faint point in the constellation Draco, hosting secrets we are only beginning to uncover. The star at the center of this planetary system has a name that astronomers use primarily for catalog purposes, rather than everyday conversation. It appears in various databases with the designation that gives the planet its own name, TRES, referring to the survey project that first detected the system. This star resembles our own Sun in many important respects, belonging to the same class of yellow dwarf stars that burn hydrogen in their cores. Yet, despite these similarities, this particular sun hosts a world utterly unlike anything orbiting our own familiar star. The stellar classification system astronomers use groups stars according to their surface temperatures and the colors of light they produce. Our Sun belongs to a category called G-type, which includes stars with surface temperatures between roughly 5,000 and 6,000 Kelvin. These stars appear yellow-white to human eyes and emit radiation strongly across the visible spectrum, making them excellent for illuminating planets. The star hosting TRES 2b falls into this same category, appearing essentially sun-like when viewed through telescopic instruments. Surface temperature for this distant star runs around 550 Kelvin hotter than our Sun, making it slightly brighter and more luminous overall. This small temperature difference translates into noticeably more energy output, perhaps 20 to 30% more light than our Sun produces each second. A planet orbiting at Earth's distance from this star would receive correspondingly more radiation and become somewhat warmer than our home world. Of course, TRES 2b does not orbit at anything close to Earth's distance, which is precisely why conditions there are so extreme. The mass of this star exceeds our Sun's mass by a small but meaningful amount, perhaps 10 to 15% heavier, according to current estimates. Greater mass means stronger gravitational pull, which affects how quickly planets orbit and how stable their trajectories remain over time. The star has likely burned through its core hydrogen supply for several billion years already, similar to the age of our own Sun. Stars like this one have total lifetimes of roughly 10 billion years before exhausting their fuel and beginning to change dramatically. Looking at this star through a small telescope would reveal nothing special, just another faint point of yellow-white light among thousands visible in the constellation Draco. The star lacks a traditional name from ancient astronomy because it was never bright enough for casual observers to notice or catalogue individually. Only modern surveys that measured the brightness and position of millions of stars brought this particular sun to scientific attention at all. The presence of TRES 2b around it created the only reason anyone would look closely at this otherwise unremarkable stellar dot. The distance between us and this star stretches across roughly 750 light-years of mostly empty space, with occasional dust and gas clouds drifting between. Light traveling at 300,000 kilometers per second needs 750 years to cross this gulf, a journey that puts cosmic scales into humbling perspective. When the light we detect tonight first left that star's surface, European civilization was experiencing the high Middle Ages and would not see the Renaissance for centuries. The simple observation of this light connects our present moment to a vastly distant past, bridging time as well as space. The constellation Draco itself sprawls across the northern sky, one of the larger constellations visible from temperate latitudes throughout the year. Ancient Greeks saw these stars as representing Ladon, the dragon that guarded the golden apples in the Garden of the Hesperides, from their mythology. Other cultures imagined different figures, but the serpentine shape, winding between Ursa Major and Ursa Minor, has carried dragon associations for millennia. Within this ancient pattern, invisible to unaided eyes, but present nonetheless, the star hosting our dark planet quietly shines. Finding this star in the sky would require a telescope and knowledge of its precise coordinates, information available in astronomical databases for anyone curious enough to look. The star carries the catalogue designation GSC 03892-01-942 in one commonly used naming system, though simpler references exist. Pointing a modest telescope at the correct location would reveal a faint point of light, indistinguishable from countless other faint stars nearby. Only the knowledge of what orbits there makes this particular point special among all the others visible in that direction. The relationship between star and planet in this system differs dramatically from anything we experience in our own solar neighborhood around the Sun. Earth orbits our Sun at an average distance of about 150 million kilometers, a span we call 1 astronomical unit for convenient reference. TRES 2b orbits its star at approximately 5 million kilometers, more than 30 times closer than Earth orbits the Sun. At this proximity, the star dominates the planetary environment in ways difficult to fully appreciate from our distant perspective. The orbital distance of TRES 2b sits well inside the orbit of Mercury, the closest planet to our own Sun, at an average of 58 million kilometers out. Mercury already experiences extreme temperature swings and intense solar radiation at that distance from our relatively modest Sun. TRES 2b, orbiting a slightly more luminous star at less than 1/10 of Mercury's distance, receives radiation intensity hundreds of times greater than Mercury. The energy pouring onto the planet's day side every second staggers the imagination when considered in full. At such close range, the gravitational relationship between star and planet becomes intensely personal, with tidal forces stretching and pulling at planetary structure constantly. The gravitational attraction at the planet's star-facing side significantly exceeds the attraction at the far side, creating a difference that distorts the planet's shape subtly. Over time, this tidal interaction drains energy from the planet's rotation, slowing any independent spin until the same face always points toward the star. This condition, called tidal locking, means TRES 2b has permanent day and night hemispheres that never change positions. We will explore tidal locking in greater detail as our journey continues. But for now, the key insight is that proximity creates this locked configuration inevitably. Any planet orbiting this close to a star will eventually become tidally locked, just as our moon has become locked to Earth over billions of years. The timescale for locking depends on distance and mass, but at TRES 2b's orbital distance, locking would have occurred relatively quickly after the planet arrived. This means the conditions we observe today, the extreme heat on one face and permanent darkness on the other, have persisted for eons. The light from this star bathes the permanently facing hemisphere of TRES 2b in continuous illumination that never dims or pauses. There is no sunrise or sunset on this world, no daily cycle of light and darkness, no respite from the stellar radiation pouring down. The same regions of atmosphere receive constant heating, while other regions never see the star directly at all, creating dramatic differences across the planet. These differences drive atmospheric circulation patterns that carry heat from day to night in complex flows we can only model imperfectly. From the planet's perspective, the star would appear enormous, spanning a significant portion of the visible sky, rather than appearing as a small disk like our Sun from Earth. Simple geometry explains this, since the apparent size of any object increases as you move closer to it, and TRES 2b is very close indeed. The star might cover roughly 20 times more sky than our Sun does from Earth's surface, dominating the dayside view with its blazing presence. Standing beneath such a star, if standing were somehow possible in this hostile environment, would feel like being inside a furnace, open to infinity. The energy transfer from star to planet happens through radiation crossing the relatively small gap between them, at the speed of light, continuously. Every second, enormous amounts of energy leave the stellar surface and travel the short distance to splash against the planet's absorbing atmosphere. Most of this energy gets converted to heat rather than reflecting back, which is what makes the planet so dark and so hot simultaneously. The star pours out light, the planet swallows that light, and the result is an equilibrium temperature of around 1800 Kelvin on the day side. Understanding this stellar environment helps explain why TRES 2b became the world we observe rather than some other kind of planet entirely. A gas giant at this distance from any sun-like star would necessarily become intensely heated and likely develop the atmospheric conditions that absorb, rather than reflect, light. The combination of stellar proximity and gas giant composition creates the essential conditions for extreme darkness and thermal glow together. Change either factor significantly, and you would get a very different kind of world as the result. The star will not remain unchanged forever, though the timescales involved stretch far beyond human comprehension or concern at present. Eventually, perhaps 5 billion years from now, the star will exhaust its core hydrogen and begin swelling into a red giant phase. During that expansion, the star might engulf TRES 2b entirely, ending the planet's existence within stellar atmosphere, turned thick and hot. Before that happens, the increasing luminosity of an aging star would heat the planet even further beyond its already extreme temperatures. For now, the system remains stable, the star burning steadily, the planet orbiting closely, the light traveling toward us across centuries of empty space. Each observation we make captures a snapshot of this relationship at a particular moment, a moment that occurred 750 years before we examine the data. The star shines, the planet absorbs, and both continue their cosmic partnership without any awareness of the distant world, where scientists puzzle over what they represent. The discovery of this planetary system required patient watching and careful analysis, skills that astronomers have refined over decades of exoplanet hunting. How TRES 2b was first detected and what scientists learned from that detection forms the next chapter of our journey through understanding. The instruments and methods that revealed this dark world tell their own story of human ingenuity applied to cosmic questions far beyond easy answering. The discovery of TRES 2b came through a straightforward but powerful technique that astronomers had been perfecting throughout the early 21st century. This technique relies on watching stars for tiny dips in brightness that occur when a planet passes between the star and our line of sight. When such a crossing happens, the planet blocks a small fraction of the starlight, and sensitive instruments can detect this temporary dimming. The method works best for large planets orbiting close to their stars, which describes TRES 2b perfectly. The name TRES comes from the Transatlantic Exoplanet Survey, a collaborative project using small telescopes on both sides of the Atlantic Ocean to monitor stars. These telescopes were not large or expensive by astronomical standards, but they could watch many stars simultaneously, night after night, without interruption. The goal was simple but ambitious: to catch the telltale brightness dips that reveal planets passing in front of their host stars periodically. Between 2006 and 2007, the project achieved one of its notable successes with the detection of this system. The brightness variations that revealed the planet's presence were subtle but consistent, repeating every 2.47 Earth days without fail. Each time the planet passed in front of its star from our vantage point, the star's brightness dropped by approximately 1.6% briefly. This might sound like a small change, but modern instruments can detect variations much smaller than this, making the signal quite robust and reliable. The regularity of the dips confirmed that something was orbiting the star with a period of just under 2.5 days. The size of the brightness dip told astronomers approximately how large the planet must be relative to the star it was crossing. A larger planet blocks more light, creating a deeper dip, while a smaller planet creates a shallower one that might escape detection entirely. The 1.6% drop indicated a planet roughly the size of Jupiter, large enough to block a meaningful fraction of the stellar disk during transit. Combined with the orbital period, this gave researchers a basic picture of what kind of world they had discovered. Additional observations using the radial velocity method confirmed the discovery and added important information about the planet's mass and true nature. This complementary technique looks for tiny wobbles in the star's position caused by the gravitational tug of an orbiting planet pulling back on its host. The star and planet actually orbit a common center of mass, and careful measurements can detect the star's slight motion even when the planet itself remains invisible. These measurements showed that the planet had a mass similar to Jupiter, confirming it as a gas giant rather than a rocky world. The initial discovery in 2006 and 2007 established TRES 2b as a hot Jupiter, a fascinating category of planet that had surprised astronomers ever since the first examples were found. Hot Jupiters orbit their stars at distances far closer than anyone expected giant planets to exist, defying early theoretical predictions about planetary formation. Finding another one added to the growing population of these strange worlds, but nothing yet hinted at the extreme darkness that would later make this planet famous. The revelation of extraordinary darkness came several years later, when the Kepler Space Telescope turned its attention to this already known planetary system. Kepler launched in 2009 with a primary mission to discover Earth-like planets around other stars using the same transit method that had found TRES 2b. The spacecraft carried instruments far more sensitive than ground-based telescopes, capable of detecting much fainter signals and much smaller variations in stellar brightness. These capabilities allowed measurements that would have been impossible from beneath Earth's turbulent atmosphere. Kepler observed the star hosting TRES 2b as part of its wide field survey of a region in the constellations Cygnus and Lyra, which overlapped with Draco. The spacecraft measured not just the brightness dips during transits, but also the subtle variations in total system brightness as the planet orbited around to different positions. When the planet's illuminated day side faced toward Earth, the total system brightness should increase slightly as reflected starlight added to the star's own output. Kepler was sensitive enough to detect this tiny additional light, or in this case, to notice its conspicuous absence. The expected reflected light signal simply was not there, or was so faint as to be barely detectable above the noise floor of the measurements. This absence told researchers that the planet was not reflecting starlight the way other planets do, that something unusual was happening with this particular world. Analysis of the Kepler data, published in 2011, revealed that TRES 2b reflects less than 1% of the light reaching it. This made it immediately the darkest known planet, a record it continues to hold more than a decade later. The discovery announcement generated considerable interest in the astronomical community and beyond, because such extreme darkness had not been predicted or expected. Scientists had models for hot Jupiter atmospheres that predicted various degrees of reflectivity, but nothing suggested values this low would occur naturally. The measurement challenged existing understanding and prompted new theoretical work to explain what physical conditions could produce such a dark world. Various possibilities emerged, involving atmospheric chemistry, temperature effects, and the absence of reflective cloud layers. The lead author of the original darkness discovery paper, David Kipping, worked at the Harvard-Smithsonian Center for Astrophysics. when the results were published. His team carefully analyzed the Kepler data to extract the tiny signals that revealed the planet's reflective properties against the bright stellar background. The analysis required sophisticated techniques to separate the planet's contribution from stellar variations and instrumental effects that might masquerade as planetary signals. The rigor of this work gave the scientific community confidence that the extreme darkness measurement was real rather than some artifact or error. Since 2011, additional observations and analyses have confirmed the essential findings while refining some details and exploring remaining uncertainties. The planet really is extraordinarily dark, though the precise reflectivity value has some uncertainty, depending on exactly how the measurements are interpreted. Various research groups have proposed explanations involving sodium, potassium, titanium oxide, and other compounds that absorb visible light efficiently at high temperatures. No single explanation has gained universal acceptance, leaving the exact cause of the darkness still partially mysterious. The discovery process exemplifies how exoplanet science builds knowledge incrementally through multiple observations, using different techniques and instruments. First came the ground-based transit detection that revealed a planet existed and determined its size and orbital period. Then came radial velocity measurements that confirmed the discovery and determined the planet's mass and nature as a gas giant. Finally came space-based photometry that revealed the unexpected darkness, setting this world apart from all others known. Each stage required patience, careful analysis, and healthy skepticism about results, until they could be confirmed through independent methods and observations. The scientific community does not accept extraordinary claims without extraordinary evidence, and the darkness of TRES 2b certainly qualified as extraordinary. The confirmation through multiple analyses and the absence of any compelling alternative explanation have made this measurement as secure as such things can be. We know this planet is dark because multiple lines of evidence all point to the same conclusion independently. The instruments that made this discovery possible represent decades of technological development in detector sensitivity, data processing, and observational strategy. The Kepler spacecraft carried a photometer capable of measuring brightness changes of a few tens of parts per million across more than 150,000 stars simultaneously. No previous instrument had achieved this combination of precision and scale, and the mission revolutionized exoplanet science during its operational lifetime. TRES 2b was just one of thousands of worlds Kepler helped characterize during its productive years of observation. Ground-based follow-up observations continue to study this system, seeking additional details about the planet's atmosphere, temperature distribution, and orbital dynamics. New instruments on large telescopes can measure the spectra of exoplanet atmospheres as starlight filters through them during transits, revealing chemical compositions directly. The James Webb Space Telescope, launched in 2021, offers unprecedented capabilities for such atmospheric characterization studies. TRES 2b may yet reveal more of its secrets to these powerful new observational tools as researchers continue their investigations. The story of discovering this dark world connects to the broader story of hot Jupiters as a class, worlds that surprised astronomers when first detected. Understanding what hot Jupiters are and why they exist helps explain why TRES 2b has the properties we observe. and measure. These giant planets, orbiting impossibly close to their stars, form a category that challenged planetary formation theories and expanded our understanding of what planetary systems can become. The first hot Jupiter ever discovered, a planet called 51 Pegasi b, announced its presence to the scientific world in October 1995. This discovery shocked astronomers because no one had expected giant planets to exist so close to their parent stars, a zone thought too hot for gas giant formation. The planet orbits its star in just 4.2 days, moving faster than Mercury orbits our own sun, a configuration that seemed impossible under prevailing theories. Yet the evidence was solid, the discovery was confirmed, and planetary science had to adapt its models to accommodate this unexpected reality. Before 51 Pegasi b, scientists assumed other planetary systems would resemble our own solar system in basic architecture and arrangement of planet types. Rocky planets would orbit close to the star where temperatures allowed solid materials to survive during formation, while gas giants would remain far out where ices could accumulate. Jupiter orbits our Sun at about 778 million kilometers, taking nearly 12 years to complete each trip around the stellar neighborhood. Saturn lies even further out, and the ice giants Uranus and Neptune occupy the distant cold regions beyond. This neat arrangement made sense given how planets were thought to form from disks of gas and dust swirling around young stars. Close to the star, only rock and metal could condense from the hot nebular material, leading to small rocky planets like Mercury, Venus, Earth, and Mars. Beyond a distance called the frost line, water and other volatiles could freeze into ice, dramatically increasing the solid material available for planet building. These icy cores could grow large enough to capture vast atmospheres of hydrogen and helium gas, becoming gas giants like Jupiter and Saturn. The discovery of hot Jupiters forced scientists to recognize that planets do not necessarily stay where they form, that migration through the protoplanetary disk can relocate giant planets dramatically. A gas giant forming beyond the frost line could spiral inward through gravitational interactions with the remaining disk material, eventually settling into a close orbit. This migration process might take millions of years, gradually moving the planet from the cold outer reaches to the scorching inner regions near the star. Once the disk dispersed, the planet would be stranded in its new location, becoming the hot Jupiter we observe today. TRES 2b almost certainly reached its current orbit through this kind of migration, rather than forming in place at such an extreme location. No plausible formation mechanism could create a gas giant at only 5 million kilometers from a sun-like star where temperatures are far too high for ices. The planet must have formed somewhere in the outer reaches of its system, accumulated its massive atmosphere of hydrogen and helium, then spiraled inward. During that journey, it may have scattered or consumed any smaller planets that had formed in the inner system ahead of its arrival. The migration hypothesis explains not only where hot Jupiters ended up, but also why they tend to be solitary, lacking companion planets in their systems. The gravitational disruption caused by a migrating giant would destabilize the orbits of smaller bodies, either flinging them out of the system or sending them plunging into the star. By the time the giant settled into its final close orbit, the inner system would be cleared of anything that had previously occupied that region. TRES 2b appears to be alone around its star, consistent with this pattern of migration-related clearing. Hot Jupiters like TRES 2b represent only a small fraction of the planetary systems astronomers have discovered, perhaps 1% or less of stars hosting such worlds. Most Sun-like stars either lack giant planets entirely or have them in more distant orbits, resembling our own solar system's arrangement. The rarity of hot Jupiters makes each one scientifically valuable, a window into extreme planetary conditions that only a few systems provide. TRES 2b, with its record-breaking darkness, offers particularly unusual insights among an already unusual category of worlds. The mass of TRES 2b sits close to Jupiter's mass, perhaps slightly larger, according to various estimates based on radial velocity measurements. This similarity in mass, despite vastly different environments, illustrates how the same amount of material can produce very different planetary outcomes depending on location. Jupiter remains cold and cloud-covered at its distant orbit, reflecting more than half the sunlight reaching it through ammonia ice crystals. TRES 2b absorbs nearly everything at its close orbit, its atmosphere stripped of clouds and filled instead with light-swallowing chemicals. The size of TRES 2b, meaning its physical diameter rather than its mass, exceeds Jupiter's diameter by a noticeable margin, despite similar masses. This inflation occurs because the intense stellar heating causes the planet's atmosphere to expand, puffing up like a balloon exposed to warmth. Many hot Jupiters show this radius inflation effect, appearing larger than they should based on mass and composition alone, without external heating. The effect provides additional evidence for the extreme temperatures these worlds experience throughout their atmospheric volumes. Gas giant planets, like TRES 2b, lack any solid surface in the traditional sense, instead consisting of progressively denser layers of gas, transitioning gradually toward a compressed core. The outer atmosphere we can study through transit observations represents only the topmost portion of a vast envelope of hydrogen and helium, extending deep within. Pressure and temperature increase steadily with depth until the gas becomes dense enough to behave more like liquid than atmosphere. Eventually, thousands of kilometers down, a core of heavier elements likely exists, perhaps rocky, perhaps metallic, perhaps a compressed mixture. This internal structure makes questions like where the surface is rather meaningless for worlds like TRES 2b, since there is no boundary between atmosphere and ground. Instead, scientists define reference levels based on pressure, often choosing the depth, where pressure equals 1 bar, similar to sea level pressure on Earth. Above this reference level lies what we call atmosphere. Below it lies the deep interior that no observation can directly probe. The darkness we measure affects only the uppermost layers, where incoming starlight interacts before being absorbed. Hot Jupiters fascinate planetary scientists precisely because they represent such extreme versions of giant planet evolution and atmospheric physics. The intense heating creates conditions impossible to study in our own solar system, where no comparable worlds exist at similar distances from the Sun. By examining hot Jupiters around other stars, researchers learn about atmospheric chemistry, circulation patterns, and physical processes that expand understanding beyond our local examples. TRES 2b contributes specifically to understanding how dark a planet can become under such extreme thermal conditions. The population of known hot Jupiters continues to grow as surveys discover more planetary systems and as improved techniques characterize known systems more precisely. Each new example adds data points that help scientists understand what factors determine planetary properties, like reflectivity, temperature distribution, and atmospheric composition. Patterns emerge from comparing many worlds, revealing which outcomes are common and which are rare or unique. TRES 2b's extreme darkness remains unusual even among hot Jupiters, suggesting particular conditions that other similar planets do not share. The orbital speed of TRES 2b represents one of the more striking characteristics that distinguish this world from familiar planets in our own solar system. Completing a full circuit around its star in just 2.47 Earth days requires tremendous velocity, far exceeding what any solar system planet achieves. This racing orbit creates effects beyond simple speed records, influencing tidal forces, atmospheric dynamics, and the overall planetary environment profoundly. At its orbital distance of approximately 5 million kilometers from the star, TRES 2b moves at roughly 200 kilometers per second to maintain its circular path. This velocity is about 7 times faster than Earth orbits the Sun, and considerably faster than even Mercury, our solar system's speediest planet. The planet effectively races around its star, completing nearly 150 orbits in a single Earth year, while we complete just one. A year on TRES 2b lasts less than 60 hours by Earth's measurement of time. The physics behind this rapid orbit involves the basic relationship between distance, speed, and gravitational attraction that governs all orbital motion. Objects closer to a gravitating body must move faster to avoid falling inward, maintaining the balance between forward velocity and gravitational pull. The orbital velocity formula depends on the mass of the central body and the orbital distance, with closer orbits requiring higher speeds invariably. TRES 2b's extreme proximity to its star demands this extreme speed as an inevitable consequence. To maintain a circular orbit at 5 million kilometers from a star similar in mass to our Sun requires precisely the velocity that TRES 2b achieves naturally. Any slower, and the planet would spiral inward, eventually falling into the star over astronomical timescales. Any faster, and the planet would swing outward to a larger orbit, where its increased distance would require less speed. The current balance represents a stable configuration that has likely persisted for billions of years since the planet arrived through migration. The short orbital period means that from TRES 2b's reference frame, the star appears to complete a full circuit of the sky every 2.47 days. Of course, this is not quite what happens, because tidal locking keeps one face always pointed toward the star, so the star does not actually move across the sky at all. Instead, the star simply hangs motionless at the same point in the sky, perpetually fixed in place by the rotational lock matching orbit and spin. The rapid orbit translates into rapid rotation, rather than apparent stellar motion across the planetary sky. The gravitational forces between star and planet at this close range dwarf anything experienced by planets in our solar system at their distances. Tidal forces, the difference in gravitational pull between the near and far sides of an extended body, stretch and distort the planet constantly. These forces have long since locked the planet's rotation to match its orbital period, eliminating any independent spin that might have existed initially. The lock ensures permanent hemispheric conditions, one side always sunlit and one side always dark, without variation. Energy dissipation from tidal heating may contribute additional warmth to the planet's interior, beyond what stellar radiation provides at the surface. As tidal forces flex and distort the planet slightly, friction within the deep layers converts orbital energy into heat that radiates outward eventually. Jupiter's moon Io experiences extreme tidal heating from its orbital relationship with Jupiter, creating volcanic activity that resurfaces the moon constantly. TRES 2b likely experiences some tidal heating as well, though stellar radiation dominates its thermal budget by far. The orbital path of TRES 2b is not perfectly circular, but likely has a small eccentricity, a slight elongation that takes the planet closer and further from the star periodically. Even small eccentricities create variations in stellar distance that translate into variations in received radiation and experienced gravitational forces. The exact eccentricity remains somewhat uncertain, given observational limitations, but most estimates suggest a nearly circular orbit, consistent with theoretical expectations. Tidal forces tend to circularize orbits over time, smoothing out any initial eccentricity through energy dissipation. At closest approach to the star, called periapsis, the planet would experience slightly more intense radiation and slightly stronger tidal forces than at its farthest point. These variations would modulate atmospheric temperatures and internal stresses on timescales matching the orbital period, creating subtle 2.5-day cycles. Observations have not yet detected these variations clearly, partly because the orbital eccentricity appears quite small, and partly because observational precision has limits. Future measurements with more sensitive instruments might reveal these orbital modulation effects. The short orbital period made TRES 2b relatively easy to detect through the transit method, compared to planets with longer orbital periods that transit less frequently. Each transit provides one opportunity to study the planet, so a planet that transits every 2.5 days offers more than 140 opportunities per Earth year. This frequency allowed astronomers to accumulate many transit observations quickly, improving the precision of their measurements through statistical averaging. A planet transiting once per year would take decades to accumulate comparable data. The orbital characteristics of TRES 2b exemplify what makes hot Jupiters valuable laboratories for studying planetary physics under extreme conditions. No planet in our solar system experiences such close stellar proximity, such intense radiation, such strong tidal forces, or such rapid orbital motion. By studying these distant worlds, scientists explore parameter space inaccessible, closer to home, testing theories against conditions that push physical models to their limits. The insights gained apply not only to hot Jupiters specifically, but to understanding planetary physics more broadly. The orientation of the orbit relative to our line of sight allows transits to occur, meaning we view the system nearly edge-on by fortunate coincidence. Only a small fraction of planetary systems are aligned such that transits are visible from Earth, with most systems tilted such that the planet never passes between star and observer. The probability of transit alignment depends on stellar size and orbital distance, with close orbits more likely to transit than distant ones. TRES 2b's close orbit gave it relatively favorable odds of transiting from our viewpoint. Each transit lasts approximately 2 hours as the planet crosses the stellar disk from our perspective, blocking light continuously during that passage. The transit begins when the planet's leading edge first touches the stellar disk, proceeds through a central phase where the planet fully overlays the star, and ends when the trailing edge departs the stellar disk completely. The depth of the brightness dip remains constant throughout the central phase, when the full planetary disk blocks light, then ramps gradually at ingress and egress. These details allow astronomers to determine planetary size, orbital parameters, and other characteristics precisely. Between transits, the planet orbits around to positions where we view its illuminated day side to varying degrees as it moves relative to the star. At greatest elongation, the day side faces toward us, while the planet appears beside the star rather than in front of or behind it. This is when reflected light should be most detectable, though TRES 2b reflects so little that the signal remains extremely faint, even at optimal geometry. The phase variations that Kepler sought to measure for this planet revealed the extreme darkness that makes it famous. When the planet passes behind the star, an event called secondary eclipse, the total system light decreases by the planet's contribution to the combined signal. For most planets, this includes both reflected starlight and thermal emission from the planet's own heat, both contributing to visibility. For TRES 2b, the reflected component is negligible, and only thermal emission contributes meaningfully to the secondary eclipse depth. Measuring this depth provides direct information about the planet's temperature distribution across its observable hemisphere. The relationship between rapid orbit and intense heating forms a self-reinforcing cycle that helps explain the planet's extreme nature comprehensively. Close orbit means strong radiation, which means high temperature, which means no reflective clouds, which means dark absorption, which means even higher temperatures as energy gets trapped. The orbital characteristics we can measure connect directly to the atmospheric properties that make this world so unusual among all known planets. Everything ties together through the basic physics of how planets interact with nearby stars. As the planet continues racing around its star, the same face always turned toward the light, we move naturally toward understanding what this tidal locking means. The division into permanent day and permanent night creates two fundamentally different environments on a single world. This locked configuration reveals how gravitational forces shape planetary rotation over astronomical timescales, connecting TRES 2b to examples closer to home. The tidal locking of TRES 2b means that one hemisphere of this planet has faced its star continuously for eons beyond human comprehension or measurement. The same face that pointed toward the stellar furnace a billion years ago points toward it still, and will continue pointing toward it for billions of years to come. The opposite hemisphere has experienced unbroken darkness for equally vast spans of time, never glimpsing the star that dominates its sibling sky. This division into permanent day and permanent night shapes every aspect of the planet's atmospheric behavior and thermal environment. Tidal locking occurs through a gradual process that drains rotational energy from a spinning body through gravitational interaction with a nearby partner. When TRES 2b first arrived in its close orbit through migration from the outer reaches, it likely still rotated independently on its axis. The star's gravity created a slight bulge on the planet's near side, pulling more strongly on the closer material than on the distant material. As the planet rotated, this bulge tried to realign with the star, but could not keep up with the rotation, creating friction that dissipated energy. This friction slowly but inexorably reduced the planet's rotation rate over millions of years until rotation and orbit matched precisely, eliminating the lag between bulge and gravitational pull. Once locked, the configuration became stable, with no further energy dissipation needed to maintain alignment. The same face now always points toward the star. The tidal bulge sits directly beneath the stellar position, and the system reaches equilibrium. Any perturbation that tried to disrupt this lock would immediately create restoring forces that return the planet to aligned rotation. The timescale for tidal locking depends on orbital distance, planetary size and rigidity, and the mass of both bodies involved in the gravitational interaction. At TRES-2b's extreme proximity to its star, the tidal forces are strong enough that locking likely occurred within just a few million years of arrival. This is geologically brief, meaning the planet has been locked for essentially its entire history at this orbital location, billions of years of unchanging orientation. The locked state is not recent or fragile, but ancient and deeply established. Our own moon provides a familiar example of tidal locking that operates through identical physics in our own celestial backyard. The moon rotates once on its axis in exactly the same time it takes to orbit Earth, about 27.3 days for each complete cycle. This synchronization means we always see the same face of the moon from Earth, the familiar pattern of dark Maria and bright highlands that humans have watched since before history began. The far side of the moon remained unknown until spacecraft photographed it in 1959. Hidden by the same tidal locking mechanism, the moon became locked because Earth's gravity raised tidal bulges in lunar rock that dissipated rotational energy through internal friction over billions of years. The process is essentially complete now, with the moon's rotation and orbit synchronized to high precision, maintained indefinitely. The same physics operating between planet and star produces identical results for TRES-2b, just on faster timescales due to stronger tidal forces at closer range. Tidal locking is universal wherever conditions allow gravitational partners to interact over sufficient time. The consequences of tidal locking for TRES-2b extend far beyond simple rotation matching to affect every aspect of planetary climate and atmospheric dynamics. The permanent day side receives constant stellar radiation at intensities that would sterilize any Earth-like surface within moments of exposure. The permanent night side never sees the star directly, remaining dark except for whatever faint glow the planet itself produces through thermal emission. Between these extremes lies the terminator, a ring girdling the planet where the star hangs perpetually on the horizon. The temperature difference between permanent day and permanent night would be even more extreme without atmospheric circulation to redistribute heat across the planet. TRES-2b has a substantial atmosphere of hydrogen and helium that can carry thermal energy through wind patterns flowing from hot regions to cooler ones. Hot gas rises on the day side where stellar heating is most intense, flows toward the night side at high altitude, cools and sinks in the darkness, then returns along the surface. This circulation cell, or possibly multiple cells, moderates the temperature contrast between hemispheres. Despite this heat redistribution, significant temperature differences likely persist between the day side and night side of this locked planet. Models suggest the day side reaches approximately 1800 Kelvin, while the night side may cool to around 1000 Kelvin, or perhaps somewhat higher. This 500 to 800 degree difference drives the atmospheric circulation that exists, with heat flowing down the temperature gradient from hot to cool perpetually. The winds carrying this heat may reach supersonic speeds in the jet streams between hemispheres. The substellar point, located at the center of the permanent day side, directly beneath the fixed star, marks the hottest location on the planet's surface. Here, the star shines from directly overhead, its radiation striking perpendicular to the atmosphere and delivering maximum intensity per unit area. Moving away from this central point toward the limbs, where the surface curves away, the effective stellar intensity decreases as the angle of illumination becomes more oblique. At the terminator, the star appears on the horizon, and the heating intensity drops dramatically compared to the substellar point. The antistellar point lies at the exact center of the permanent night side, as far from the star as any location on the planet can possibly be. This region has never seen the star directly, receives no direct radiation, and would be the coolest part of the planet, if not for atmospheric heat transport. Instead, circulating winds carry warmth from the day side even to this most remote location, preventing temperatures from dropping as low as pure darkness would suggest. The night side still glows faintly in the infrared, evidence that heat reaches it despite the permanent absence of direct stellar illumination. The terminator zone itself presents unique conditions that lie between the extremes of permanent day and permanent night. Here, the star remains on the horizon perpetually, neither rising nor setting, casting long shadows that never shift or shorten. The illumination intensity is lower than on the central day side, but present nonetheless, creating twilight conditions around the entire circumference of the planet. Atmospheric dynamics at the terminator may differ from both day side and night side, influenced by the horizontal radiation geometry. Tidal locking creates a fundamentally different planetary experience than anything familiar from Earth or the other solar system planets we know well. On Earth, day and night alternate regularly as the planet rotates, distributing solar heating around the globe in a daily cycle. Seasons change as Earth's tilted axis points different hemispheres toward the Sun during the annual orbit, creating longer and shorter days, predictably. Nothing about TRES 2b resembles this dynamic, rhythmic pattern that governs earthly experience so fundamentally. Instead, TRES 2b exists in a state of frozen time, at least regarding day and night, where conditions persist unchanged through eons, without variation. The day side remains day, the night side remains night, and the terminator remains twilight, in eternal stasis that rotates nothing internally. Only the 2.5-day orbit around the star moves the planet through space. But this motion changes nothing about which hemisphere faces which direction. The same atmospheric circulation, the same temperature distribution, the same conditions persist without the cycles that characterize Earth. This locked state would have profound implications for any atmospheric chemistry or potential photochemistry occurring on the planet's day side. Continuous illumination means continuous driving of any light-dependent chemical reactions, without the nightly pause that Earth's rotation provides. The atmosphere on the day side has had billions of years of uninterrupted stellar exposure to reach whatever chemical equilibrium high temperatures and constant radiation produce. The night side, conversely, has had billions of years of darkness to develop whatever chemistry occurs without stellar input driving reactions. The locked rotation also means that any observer stationed on the day side would see the star in the same position in the sky forever, unchanging. There would be no sunrise to mark a new day, no sunset to signal approaching rest, no movement of celestial bodies across the sky to measure passing time. The star would hang motionless, enormous and brilliant, at whatever elevation corresponds to the observer's latitude on the permanent day side. Time would pass, but the sky would give no indication of its passage whatsoever. An observer on the night side would experience even stranger conditions, with a sky that never shows the system's star at all, despite orbiting it constantly. The stars of the background galaxy would be visible, rotating slowly overhead as the planet completes its orbit around the star it cannot see. But no local sun would ever rise above the horizon. No warmth would arrive directly from above, and the only heat would come carried by winds from the hidden dayside. This permanent darkness would be unlike any night on Earth, which always promises eventual dawn. The Terminator observer would see something different again, with the star perpetually on the horizon in whichever direction faces the day side. Half the sky would be the darkness of the night side, half would be the glow of the permanently illuminated hemisphere beyond the horizon. The star itself might be visible as a brilliant point on the horizon, never rising higher, never setting lower, frozen in place. Shadows would stretch infinitely long across the surface, never shortening as no noon ever arrives. These thought experiments help illustrate how profoundly different a tidally locked world would feel compared to anything in human experience or Earth-based intuition. Every aspect of daily life on Earth depends on the regular alternation of light and dark that rotation provides, from sleep cycles to plant growth. A world without this alternation would require completely different approaches to any process that relies on day-night cycling for its rhythm. TRES 2b represents an extreme example of conditions that differ fundamentally from the planetary environments humans evolved within. The physics of tidal locking will continue to operate on this planet, essentially forever, maintaining the current orientation until something dramatic changes the system. The star will eventually evolve, expanding and changing luminosity as it ages through its stellar life cycle, over billions of years still to come. When that happens, the tidal forces on TRES 2b will change as well, potentially altering the locked state in ways that depend on specifics of stellar evolution. For now, and for the foreseeable future, the lock persists, unchanged. TRES 2b will continue facing its star with the same hemisphere, absorbing radiation on the same region of atmosphere, circulating heat through the same patterns endlessly. The permanent day will remain permanent, the permanent night will remain dark, and the Terminator will remain caught between for eons beyond human timescales. This locked world orbits in 2.5 days, racing around its star, yet, from the planet's perspective, nothing changes from one orbit to the next. The star hangs motionless, the darkness persists, and the twilight holds its endless vigil around the dividing line. Understanding tidal locking helps explain many features of TRES 2b that would otherwise seem mysterious or contradictory when viewed through Earth-based assumptions. The extreme temperature differences between hemispheres, the atmospheric circulation patterns, the chemical gradients that might exist across the planet, all trace back to this fundamental locked state. The darkness on one side and the burning brightness on the other are not temporary conditions, but permanent features built into the planet's very rotation. Everything about this world flows from the simple fact that it shows one face to its star forever. And within that permanent arrangement, the atmosphere wraps around both hemispheres, the layer of gases that makes TRES 2b so remarkably dark despite its proximity to stellar brilliance. That atmosphere, with its light-swallowing chemistry and absent reflective clouds, holds answers to why this planet absorbs nearly every photon that reaches it, a mystery that continues as we explore deeper. The atmosphere of TRES 2b presents one of the most puzzling aspects of this already strange world, a gaseous envelope that swallows light more completely than any other known planetary atmosphere. Most planets and moons reflect significant portions of the light that reaches them, bouncing photons back into space to make them visible from distant observation points. Jupiter reflects about 52% of incoming sunlight, appearing as a bright, striped sphere through even modest telescopes when properly positioned. Earth reflects roughly 30%, appearing as the famous pale blue dot when photographed from the outer solar system by departing spacecraft. TRES 2b reflects less than 1%, making it darker than coal, darker than asphalt, darker than almost any natural substance commonly encountered. Something about the chemical composition of this atmosphere, combined with the absence of reflective cloud layers, creates near-perfect light absorption. Understanding what makes this possible requires exploring atmospheric chemistry at temperatures far beyond anything in our solar system's experience. The gases that exist in this superheated environment behave differently than their cooler counterparts elsewhere. The primary components of TRES 2b's atmosphere are almost certainly hydrogen and helium, the same dominant gases found in Jupiter, Saturn, and all gas giant planets. These elements are the most abundant in the universe and form the bulk of any planet massive enough to gravitationally retain them against escape into space. Hydrogen and helium themselves are not particularly dark, with neither gas absorbing visible light strongly at any temperature or pressure. The darkness must come from other components, the trace gases and compounds that make up small percentages of the total atmosphere. At temperatures approaching 1800 Kelvin on the day side, many substances exist as gases that would be solid or liquid under cooler conditions found elsewhere. Metals, like sodium and potassium, which exist as shiny reflective solids on Earth, vaporize completely in such heat and become gaseous atoms floating in the hydrogen-helium atmosphere. Both sodium and potassium absorb visible light strongly when in gaseous form, particularly in specific wavelengths that appear as dark lines in the spectrum. These alkali metals have been detected in the atmospheres of other hot Jupiters through spectroscopic observation during transits. The presence of gaseous sodium and potassium could explain part of TRES 2b's extreme darkness, as these atoms would absorb incoming starlight across broad spectral regions. Sodium absorbs strongly in the yellow-orange part of the spectrum, while potassium absorbs in the red, and together they could remove significant portions of visible light from reflection. However, calculations suggest that sodium and potassium alone cannot fully account for the nearly complete light absorption that observations reveal. Additional absorbing species must contribute, to achieve the less than 1% reflectivity actually measured. Titanium oxide represents another candidate chemical that could contribute to the atmospheric darkness of this scorched world when present in gaseous form. On Earth, titanium oxide is familiar as the white pigment in paint and sunscreen, reflecting light strongly in solid form at room temperature conditions. At TRES 2b temperatures, titanium oxide would exist as a gas and might behave very differently, potentially absorbing light rather than reflecting it. Theoretical models of hot Jupiter atmospheres predict titanium oxide should be present in the hottest examples, though detecting it observationally remains challenging. Vanadium oxide, a related compound, could also exist in the superheated atmosphere and contribute additional light absorption across visible wavelengths when conditions allow. Like titanium oxide, vanadium oxide behaves differently in gaseous form at extreme temperatures than familiar experience with cooler solid forms might suggest. Together, these metal oxide gases could create a chemical cocktail that absorbs across broad portions of the visible spectrum, leaving little light to reflect. The exact mixture and abundances remain uncertain, but the general principle of gaseous metal compounds absorbing visible light seems well-founded. Beyond these specific absorbing chemicals, the absence of reflective clouds plays an equally important role in creating the planet's extreme darkness. Jupiter appears bright, partly because its visible surface consists of cloud layers made from ammonia ice crystals that reflect incoming sunlight efficiently, like freshly fallen snow. Saturn, similarly, has bright cloud bands, and even Neptune and Uranus show high reflectivity from methane and other icy clouds in their cold upper atmospheres. Clouds are natural reflectors, and planets with thick cloud covers tend to be brighter than those without. TRES 2b is simply too hot for any clouds to form, at least on the day side where observations primarily sample the atmospheric conditions. Ammonia clouds require temperatures around 130 Kelvin, far colder than anywhere on this scorched planet approaches even remotely. Water clouds need temperatures below about 300 Kelvin, still impossible on the day side and likely even on the cooler night side regions. Silicate clouds, made from rock vapor condensing into tiny droplets, might form at temperatures around 1500 to 1700 Kelvin, somewhere in the atmosphere. The possibility of silicate clouds on TRES 2b has attracted scientific interest because they might form on the night side where temperatures drop low enough for condensation. If rock vapor circulates from the hot day side to the cooler night side through atmospheric winds, it could condense into clouds of liquid or solid silicate droplets. These clouds would then be carried back toward the day side by return circulation, potentially evaporating again as they enter hotter regions. Such a cycle could transport heat and material around the planet while creating interesting cloud patterns on the night hemisphere. However, even silicate clouds on the night side would not affect the planet's apparent darkness much, because observations primarily measure day-side reflectivity during orbital phases when that hemisphere faces Earth. The extreme darkness refers specifically to how little light the day side reflects, and that hemisphere remains too hot for any known cloud-forming condensate. The night side might be a very different environment visually, but we see mostly the day side when measuring the planet's overall reflectivity. The darkness is fundamentally a day side phenomenon. The combination of absorbing gases and absent clouds together creates near-perfect conditions for light absorption that produce the measured reflectivity below 1%. Light entering the atmosphere encounters gaseous sodium, potassium, and possibly metal oxides that absorb across the visible spectrum before photons can scatter back towards space. Without reflective cloud particles to bounce light upward, at any atmospheric level, absorption continues until virtually all incoming energy converts to heat. The atmosphere acts as a near-ideal absorber, capturing starlight and warming further rather than reflecting it away. This extreme absorption efficiency has an interesting consequence that connects to the planet's faint red glow observed despite its darkness. A perfect absorber is also a perfect emitter, according to fundamental principles of thermal radiation that apply to all matter universally. An object that absorbs all incoming light will radiate energy back as thermal emission, with maximum efficiency at wavelengths determined by its temperature. TRES-2b absorbs nearly all incoming starlight and therefore radiates thermal energy with high efficiency, producing the faint reddish glow that makes this dark world visible. The atmosphere thus performs two functions simultaneously, absorbing incoming visible light from the star while emitting infrared and visible thermal radiation from its own heat. These are not contradictory properties, but rather complementary aspects of good absorber-emitter behavior in physical systems that exchange radiation. The darkness and the glow arise from the same underlying property, the atmosphere's efficiency at interacting with electromagnetic radiation through absorption and emission. A less absorbing atmosphere would reflect more light, but also emit less thermal radiation. Scientists continue working to understand exactly which chemicals contribute to the absorption and in what proportions they must exist to match observations precisely. Models that include sodium, potassium, titanium oxide, and vanadium oxide come close to reproducing the extreme darkness, but do not achieve perfect agreement with measurements. This suggests either that abundances differ from predictions, additional unknown absorbers contribute, or the atmospheric structure differs from simple models' assumptions. The exact recipe for such extreme darkness remains somewhat uncertain. Future observations with more sensitive instruments might reveal additional details about the atmospheric composition that explain the darkness more completely and thoroughly. Spectroscopic analysis during transits can detect absorption features from specific chemicals as starlight filters through the atmosphere's edge during the planet's passage. The James Webb Space Telescope and other advanced instruments can probe atmospheres in unprecedented detail across wavelength ranges previously inaccessible for study. TRES-2b represents an appealing target for such observations, precisely because its extreme properties make it scientifically interesting. For now, the atmosphere remains somewhat mysterious, a thick envelope of superheated gas that swallows nearly all light while glowing faintly from its own intense heat. The hydrogen and helium that form its bulk contain trace amounts of exotic chemicals vaporized by temperatures no familiar world experiences in our solar system. No clouds soften the absorption, no reflective layers bounce light back, and the result is the darkest planetary surface ever measured in any system known. This light-swallowing atmosphere wraps around both hemispheres, experiencing different conditions on the permanent day side than on the eternal night side beyond. And it is the permanent day side that hemisphere locked in endless noon, where the star blazes most intensely and conditions reach their most extreme expressions anywhere on the planet. This region absorbs the most light, reaches the highest temperatures, and drives the atmospheric circulation that distributes heat around the world through restless, superheated winds. The eternal day side of TRES 2b represents conditions more extreme than any location in our solar system, a hemisphere that has faced its star continuously for billions of years without a single sunset. The star hangs motionless in the sky above this hemisphere, blazing with intensity roughly 1,000 times greater than Earth receives from the Sun. Every square meter of the upper atmosphere absorbs this radiation constantly, heating to temperatures that would destroy any material familiar from everyday experience on Earth. This is a realm of perpetual noon, where the concept of time passing means nothing because no celestial motion marks its passage. At the center of this day side lies the substellar point, the location where the star appears directly overhead at all times, the hottest spot on the entire planet. Here, the radiation arrives perpendicular to the atmosphere, delivering maximum energy per unit area without any geometric reduction from oblique angles. Temperature at the substellar point likely reaches the highest values anywhere on TRES 2b, perhaps the full 1800 Kelvin that represents the planet's peak thermal state. From this central point, temperatures gradually decrease outward toward the limbs where the curved surface receives radiation at increasingly shallow angles. The star, as seen from the substellar point, would dominate the sky enormously, appearing roughly 26 times larger in angular diameter than our Sun appears from Earth. This is not a subtle difference, but a dramatic visual transformation that would make the star a massive presence, filling significant portions of the overhead sky constantly. The brightness would be beyond anything humans could safely observe, intense enough to damage any imaging system not specifically shielded against such overwhelming radiation flux. Looking at the star from this location would be impossible for biological eyes adapted to gentler illumination levels. Moving away from the substellar point across the permanent day side, the star would appear progressively lower in the sky as the curved planetary surface tilts away from direct overhead alignment. At locations halfway between the substellar point and the terminator, the star would appear perhaps 45 degrees above the horizon, still blazing intensely, but at a more oblique angle. The effective heating at these locations would be reduced compared to the substellar point, with temperatures perhaps a few hundred Kelvin cooler while still remaining extremely hot. The atmosphere here still absorbs enormous energy, but somewhat less than at the central hottest point. As observations approach the terminator, the boundary between permanent day and permanent night, the star would appear increasingly close to the horizon, and heating intensity would diminish further. Near the terminator, the star sits on the horizon perpetually, its rays striking the atmosphere at very shallow angles that reduce effective heating substantially. Temperatures here might be several hundred Kelvin cooler than at the substellar point, though still far hotter than any Earth environment by comfortable margins. This creates a temperature gradient across the day side from blazing center to relatively cooler edges. This temperature gradient drives atmospheric circulation patterns that carry heat away from the substellar point toward cooler regions, including the terminator and night side beyond. Hot gas rises at the substellar point where heating is most intense, creating an upwelling column of superheated atmosphere moving toward higher altitudes continuously. This rising gas must flow somewhere, spreading outward from the substellar point toward the limbs and terminator at high altitude in the atmosphere. The pattern resembles a fountain of hot gas, rising at the center and flowing outward in all directions toward the planetary edges. At the terminator and beyond, this high-altitude flow begins to cool and sink as it enters regions receiving less direct stellar radiation. The sinking gas then flows back toward the substellar point, along lower atmospheric levels, completing a circulation cell that continuously redistributes heat. This pattern, sometimes called substellar to antistellar circulation, represents one possible atmospheric flow configuration for tidally locked planets like TRES 2b. Other flow patterns involving jets and eddies likely also exist, creating complex wind systems throughout the atmosphere. Wind speeds in this circulation could be extraordinary by Earth standards, possibly reaching several kilometers per second in the fastest jet streams between hemispheres. Such winds would be supersonic, faster than sound travels through the hydrogen-helium atmosphere at these temperatures and pressures we observe. The energy driving these winds comes from the enormous temperature differences between the superheated dayside and cooler nightside regions across the planet. As long as the star continues shining and the planet remains locked, these winds will continue blowing in patterns established over billions of years. The atmosphere on the dayside exists in a state of constant turmoil, driven by the unending energy input from the nearby star perpetually overhead. Rising and falling gas parcels, horizontal winds carrying heat toward the terminator, eddies and vortices forming and dissipating continuously without rest, characterize this environment. Yet, from a human timescale perspective, this turmoil would appear constant and unchanging, the same patterns repeating indefinitely, without the variations that weather on Earth introduces. There are no seasons, no day-night cycles, no variable cloud cover to change conditions from one time to another. The chemistry of the dayside atmosphere differs from the night side due to the continuous, intense radiation driving photochemical reactions in this superheated gaseous environment. Stellar ultraviolet and visible light can break apart molecules and ionize atoms, creating reactive species that participate in chemical processes otherwise unfavorable thermodynamically. These photochemically produced species may persist at higher concentrations on the dayside than equilibrium chemistry alone would predict under these extreme conditions. The result is an atmosphere that differs chemically between the illuminated and dark hemispheres. Despite the extreme conditions, no solid surface exists on the dayside or anywhere on this gas giant planet in any conventional sense familiar from rocky worlds. TRES 2b is a gas giant like Jupiter, with an atmosphere that simply grows denser with depth, rather than terminating at a rocky or icy surface boundary. Pressure increases continuously as depth increases, eventually reaching levels where hydrogen behaves more like a liquid than a gas. Though no sharp boundary separates these phases, the surface that receives starlight is simply the altitude where the atmosphere becomes opaque to incoming radiation. This means the dayside is not a landscape, but an atmospheric region, a three-dimensional volume of superheated gas that absorbs radiation throughout its optically accessible layers. The darkness of the planet comes from this atmospheric absorption, not from any dark surface material lying beneath transparent gas layers. Light enters the atmosphere and is absorbed by gas phase chemicals before reaching any deeper level from which it might reflect upward again. The whole concept of surface reflectivity requires translation when applied to a world with no solid surface to reflect anything. The dayside atmosphere glows faintly red from its own thermal emission, the same glow that makes this dark planet visible despite its extreme light absorption properties. At 1800 Kelvin, the atmospheric gases emit radiation in the infrared, and extending into the deep red portion of the visible spectrum, weakly but detectably. This thermal glow does not require external illumination, arising instead from the internal heat of the atmosphere itself, maintained by continuous stellar heating. The dayside thus appears as a faintly glowing dark sphere, emitting its own light while absorbing nearly all incoming illumination. Heat absorbed on the dayside does not all remain there, but flows toward cooler regions through the atmospheric circulation already described in considerable detail. This heat transport prevents the dayside from reaching even higher temperatures that would occur if no redistribution existed, moderating the extreme conditions slightly. The night side receives this transported heat and warms beyond what it would reach if isolated from the dayside entirely. The planet functions as a single thermodynamic system, with energy flowing from hot to cold continuously. The permanent nature of dayside conditions means that any atmospheric features have had billions of years to reach equilibrium states, stable under constant illumination. Any processes that could occur have occurred. Any chemical reactions that could reach completion have completed, and the atmosphere has settled into whatever configuration constant conditions produce. This differs profoundly from Earth's atmosphere, which responds dynamically to changing seasons, day-night cycles, and variable solar output continuously. TRES 2b's dayside exists in a kind of eternal present, unchanging in its fundamental character. Scientists studying this dayside must rely entirely on remote observation across 750 light-years of intervening space, using instruments designed for such challenging work. Transit spectroscopy provides information about the atmosphere's composition when the planet passes in front of its star and starlight filters through atmospheric edges. Eclipse measurements, when the planet passes behind its star, reveal how much thermal emission comes from the dayside by comparing brightness with and without the planet visible. Phase curve observations track brightness changes as different portions of the planet face Earth throughout the orbit. These observational techniques have revealed the extreme darkness, estimated the temperature, and constrained the atmospheric composition to some degree for this remarkable world. Each new observation adds detail to our understanding, while also raising additional questions about processes occurring in this extreme environment, far from direct examination. The dayside of TRES 2b will remain an object of remote study for the foreseeable future, a laboratory for extreme planetary physics, accessible only through the light it fails to reflect and the heat it continually radiates toward the cosmos. Beyond the terminator, past the ring of eternal twilight, lies the opposite hemisphere, the realm of permanent night that has never seen its star since the planet became tidally locked billions of years in the past. This night side experiences conditions very different from the blazing day side, though perhaps less different than intuition might suggest, given the atmospheric connection between hemispheres. The darkness here is complete in terms of direct stellar illumination, yet heat arrives continuously from the day side through atmospheric winds, maintaining temperatures that remain extremely high by Earth standards. The night side of TRES 2b has existed in permanent darkness for longer than complex life has existed on Earth. Billions of years without a single photon of direct starlight reaching this hidden hemisphere. The star that dominates the dayside sky has never risen above the nightside horizon, remaining perpetually hidden behind the bulk of the planet itself throughout recorded time. This darkness is total and permanent, in a way that no Earth location ever experiences, where even the polar night eventually ends with the returning sun. Here there is no returning sun, because the sun never departed. It simply exists elsewhere on a world that shows one face forever. Despite this absolute darkness from the star, the night side is not cold by any reasonable standard, derived from familiar planetary experience. Atmospheric circulation carries heat from the day side continuously, warming the night side to temperatures estimated around 1000 Kelvin, or perhaps somewhat higher in the current best models. This is still roughly 727 degrees Celsius, hot enough to glow visibly in the deep red portion of the spectrum, like heated metal in a furnace. The night side is dark only in the sense of receiving no direct starlight, not in the sense of being cold or actually invisible. The anti-stellar point, located at the exact center of the night side, directly opposite the substellar point, represents the location most isolated from direct stellar heating. This is the farthest point from the star that exists anywhere on the planet, receiving whatever heat atmospheric circulation manages to transport across the entire planetary diameter. Even here, temperatures likely remain around 1000 Kelvin or above, kept warm by the restless atmosphere that carries energy from the burning day side perpetually. No location on this planet approaches cold by any familiar definition whatsoever. Moving from the anti-stellar point toward the terminator, temperatures likely increase gradually as proximity to the heated day side improves heat transport efficiency through reduced distance. Near the terminator, the night-side atmosphere may be only slightly cooler than the day-side terminator regions, with heat flowing readily across the narrow boundary between hemispheres. The temperature gradient across the night side from coolest anti-stellar point to warmest terminator regions creates its own circulation patterns within this dark hemisphere independently. Cooler gas sinks at the anti-stellar point, while warmer gas rises near the terminator, establishing circulation cells. The night side atmosphere differs chemically from the day side due to the absence of photochemical reactions driven by stellar ultraviolet and visible radiation continuously. Without constant illumination breaking apart molecules and ionizing atoms, the chemistry may be closer to simple thermodynamic equilibrium at the prevailing temperatures. Species that are photochemically destroyed on the day side may accumulate to higher concentrations on the night side, where no stellar radiation reaches to break them apart. This could create chemical gradients across the terminator as different molecular species dominate in illuminated versus dark regions. One particularly interesting possibility involves cloud formation on the night side at temperatures too hot for clouds on the day side, but potentially cool enough here. Silicate clouds, formed from condensing rock vapor at temperatures around 1500 to 1700 Kelvin, might exist in the cooler night-side regions. Hot gas carrying vaporized silicates from the day side could cool sufficiently as it circulates to the night side to allow condensation into tiny droplets or particles. These silicate clouds would be unlike any clouds in our solar system, formed from materials that are solid rock under Earth conditions. If silicate clouds exist on the night side, they would affect the atmospheric dynamics, chemistry, and appearance of this hidden hemisphere in ways still being explored theoretically. Clouds reflect and scatter light, potentially making the night side somewhat brighter in the infrared than a clear atmosphere would allow. They also release heat when they form as vapor condenses, warming the atmosphere locally and affecting circulation patterns. The clouds might be carried by winds back toward the day side, where they would evaporate again as temperatures rise above the condensation point. This cycle of evaporation on the day side, circulation to the night side, condensation into clouds, and return circulation to the day side would transport both heat and material around the planet continuously. Such processes are speculative based on theoretical models rather than direct observation, since the night side is difficult to study from Earth's distant vantage point. Phase curve observations can provide some information about night side temperatures and brightness, but detailed cloud mapping remains beyond current observational capabilities for this distant world. The sky from the night side would show the stars of the background galaxy rotating slowly overhead as the planet completes its orbit around its hidden star. One orbit takes 2.5 days, so the stars would move noticeably over hours of observation, completing a full circuit every 60 hours or so. This would be the only motion visible in a night-side sky perpetually devoid of its own system's star, the only marker of time passing in eternal darkness. The background stars themselves would appear essentially identical to how they appear from Earth. The same patterns of constellations visible across interstellar distances. The faint red glow from the night-side atmosphere would be visible looking down toward the surface, though no surface exists on this gas giant world. This glow comes from thermal emission of the 1000 Kelvin gases, faint but real illumination produced by the atmosphere's own heat rather than reflected starlight. An observer on the night side would see everything in this dim reddish light, a world of permanent darkness, illuminated only by its own thermal radiation. This is about as dim as visible light can be, while still being visible, the threshold where matter is just hot enough to glow. No human observer will ever experience the night side of TRES 2b directly, separated from us by 750 light years and conditions instantly fatal to biological life. The temperatures alone would destroy any material a human body is made of in moments, quite apart from the pressure and chemical environment being equally hostile. This world exists purely as an object of scientific curiosity, a laboratory for understanding planetary physics under conditions impossible to replicate on Earth. We study it through the photons that reach our telescopes after centuries of travel, learning about this hidden hemisphere through indirect means. The night side will continue existing in its permanent darkness as long as the planet remains in its current orbit and the star continues shining in its current state. Billions of years from now, when the star ages and evolves, conditions throughout the system will change in ways that current stability cannot suggest. The locked orientation may persist, or tidal forces may change as the star's properties shift, potentially altering the relationship between planet and star. These changes lie far in the future, beyond human concern or lifespan, relevant only to cosmic timescales that dwarf all human history. For now, the night side remains dark, warm, and mysterious, the hidden half of the darkest planet ever discovered by human instruments and analysis. It receives heat from the day side continuously, glows faintly from its own thermal emission perpetually, and may host silicate clouds in its cooler regions, theoretically. Scientists continue developing models and seeking observations that could reveal more about this unseen hemisphere's true conditions. What remains certain is that the night side of TRES 2b represents conditions unlike anything in our solar system. Extreme yet stable, dark yet warm, hidden yet known to exist. This world differs profoundly from the gas giants we know in our own solar system, separated not by fundamental physics, but by environment and history. Jupiter, the archetype of gas giant planets, orbits at such immense distance from the Sun that its conditions could not be more different from those on TRES 2b. Comparing these two worlds reveals how environment shapes what a planet becomes, transforming similar starting materials into vastly different outcomes across cosmic time. Jupiter orbits the Sun at an average distance of roughly 778 million kilometers, completing one orbit every 12 Earth years in its stately journey through the outer solar system. TRES 2b orbits its star at approximately 5 million kilometers, completing one orbit every 2.5 Earth days in its frantic race around a nearby stellar furnace. This distance difference, roughly 150-fold, explains essentially all the dramatic differences between these two gas giant planets. Environment, not fundamental nature, creates worlds so different they seem unrelated despite similar masses and compositions. Both planets formed from the same basic materials, hydrogen and helium, dominating their compositions with smaller amounts of heavier elements mixed throughout their deep interiors. Both probably have rocky cores deep within, surrounded by layers of compressed hydrogen and helium that behave differently under increasing pressure as depth increases. Both are gas giants in the technical sense, lacking solid surfaces where land and atmosphere meet in the manner familiar from rocky worlds. Yet their surface conditions, appearances, and atmospheric behaviors differ almost completely despite these fundamental similarities. Jupiter rotates rapidly on its axis, spinning once every 10 hours in a blur of motion that flattens the planet noticeably into an oblate spheroid wider at the equator than at the poles. TRES 2b rotates once every 2.5 days, locked to its orbital period by tidal forces that Jupiter's distant orbit never produces effectively. This means Jupiter experiences day and night across all its latitudes as it spins, while TRES 2b has permanent day and permanent night on fixed hemispheres perpetually. The rotation difference alone creates fundamentally different atmospheric dynamics between these worlds. Jupiter's rapid rotation creates the famous banded structure of alternating light zones and dark belts that characterize its visible appearance through any telescope. These bands represent different atmospheric conditions, with rising bright clouds in zones and sinking darker regions in belts driven by Coriolis forces from rapid rotation. TRES 2b, rotating slowly and receiving enormous external heating, likely has completely different circulation patterns, dominated by day-to-night heat transport rather than rotation-driven bands. The appearance of these two worlds from space would share almost nothing in common visually. Temperature represents the most dramatic difference with Jupiter's cloud tops averaging around 125 Kelvin, roughly minus 150 degrees Celsius, while Tres 2b's dayside reaches 1800 Kelvin. This temperature difference of over 1600 Kelvin separates frozen ammonia ice clouds from vaporized metal gas in the most fundamental way possible, thermodynamically. Jupiter is a cold world by any standard, receiving little heat from the distant sun and producing only modest internal heat from slow gravitational contraction. Tres 2b is blazingly hot, heated externally by its nearby star to temperatures that liquefy steel. Jupiter's famous appearance features colorful bands of white, tan, orange, and reddish hues created by various chemical compounds in its cloud layers at different altitudes. Ammonia ice forms the highest, whitest clouds in the bright zones where atmospheric upwelling brings fresh material to high altitudes where it condenses. Deeper clouds contain ammonium hydrosulfide and water, with colors possibly coming from sulfur compounds, phosphorus, or organic molecules created by solar radiation effects. The Great Red Spot, a storm larger than Earth that has persisted for centuries, adds distinctive character to the giant planet's appearance. Tres 2b appears almost completely black, darker than coal, reflecting less than 1% of incoming light compared to Jupiter's 52% reflectivity, measured carefully. No colorful clouds exist because temperatures are far too high for any condensate familiar from Jupiter's cold environment to form solid or liquid particles. The colors that make Jupiter beautiful simply cannot exist under conditions that vaporize every material that creates them on the colder world. Instead, absorbing gases swallow light, while the thermal glow provides the only visible emission from this dark world. Jupiter possesses the most extensive satellite system of any planet in our solar system, with 95 known moons orbiting through its gravitational influence, gravitationally bound to it. The 4 Galilean moons alone, discovered in 1610, include worlds with subsurface oceans, active volcanism, and other features of intense scientific interest to researchers. Europa may harbor conditions suitable for life beneath its icy shell, while Io experiences the most intense volcanic activity known anywhere in the solar system. These moons add richness to the Jovian system that extends far beyond the planet itself. Tres 2b almost certainly has no moons, its orbit too close to its star to allow stable satellite orbits around the planet itself for extended periods. Any moon would experience gravitational influences from both the nearby star and the planet, with the star's influence dominating at such close planetary orbital distance. Orbits that might be stable around a planet far from its star become chaotic and short-lived when the star is so close and massive relative to planetary distances. The hot Jupiter orbits alone, without companions to add complexity or interest to its system. Jupiter has been visited by multiple spacecraft across decades, from the Pioneer and Voyager flybys of the 1970s to the Galileo orbiter and Juno currently studying it in unprecedented detail. We have images of its clouds at close range, measurements of its magnetic field and radiation environment, data on its internal structure from gravitational studies, and analysis of its atmospheric composition from direct probes. Jupiter is a known world, studied extensively, photographed beautifully, understood in considerable detail through decades of dedicated exploration. We have sent machines there and received their reports back across the vast distance TRES 2b will never receive visiting spacecraft in any foreseeable human future. Separated from us by 750 light years, that even light takes 7.5 centuries to cross. Everything we know about this world comes from photons that left its star when Europe was in the Middle Ages, carrying information across intervening space to reach our instruments today. We cannot photograph its surface, measure its magnetic field directly, or send probes into its atmosphere to sample composition with certainty. This world exists purely as a remote object, known only through inference from light curves and spectra. If Jupiter were moved much closer to the Sun, it would gradually transform into something resembling a hot Jupiter like TRES 2b over astronomical timescales. The ammonia clouds would evaporate first as temperatures rose, followed by water clouds and then any remaining condensates in succession. Colors would fade as the materials creating them vaporized into transparent gases at the increasing temperatures the planet would experience. Eventually, the planet would become dark like TRES 2b, with absorbing gases replacing reflective clouds throughout its visible atmosphere. The transformation would also lock Jupiter's rotation tidally as it approached the Sun, slowing the 10-hour spin to match whatever orbital period the closer distance required through tidal friction. The banded structure would disappear as rapid rotation ceased to drive the Coriolis-dependent circulation patterns, creating the belts and zones visible today. A new circulation pattern would emerge, dominated by heat transport from a permanent dayside to a permanent nightside hemisphere. The Great Red Spot would dissipate as the atmospheric dynamics sustaining it changed fundamentally and permanently. This thought experiment illustrates that TRES 2b and Jupiter are not fundamentally different types of objects, but similar objects in different environments experiencing different fates. Both are hydrogen-helium gas giants, with rocky cores and deep atmospheric layers surrounding them in fundamentally similar structural arrangements. The differences arise from temperature, radiation, rotation, and tidal forces, all consequences of orbital distance from the parent star rather than intrinsic planetary properties. Environment shapes worlds, transforming raw materials into specific outcomes, depending on where formation and migration place them. Understanding this connection helps place TRES 2b in context within the broader family of gas giant planets across all planetary systems studied. Hot Jupiters are not alien creations, but familiar worlds in unfamiliar places. Jupiters baked and locked and transformed by proximity to stellar heat. The physics is the same, the chemistry follows the same rules, and the outcomes differ only because the conditions differ so dramatically between locations. What seems strange about TRES 2b would seem natural to any observer who understood it as Jupiter relocated rather than something fundamentally different. This comparison also highlights how special our solar system's configuration may be, with gas giants orbiting in the cold outer reaches where they presumably formed originally. Hot Jupiters must migrate inward from their formation locations, disrupting interplanetary systems and changing the architecture of their stellar neighborhoods permanently. Our Jupiter never migrated inward, remaining in its original distant orbit, where it has protected inner planets from some bombardment and influenced solar system structure. The presence of hot Jupiters elsewhere suggests our solar system's arrangement is one possibility among many, rather than a universal template. TRES 2b will continue orbiting its star as it has for billions of years, a hot Jupiter in the classic mold, dark and glowing, and tidally locked in endless repetition. Jupiter will continue orbiting our Sun at its vast distance, cold and colorful, and rapidly spinning through familiar patterns observed since Galileo first turned his telescope skyward. Both are gas giants. Both are mostly hydrogen and helium. Both have rocky cores deep within, but their experiences could not differ more completely due to circumstance. What a planet becomes depends not just on what it is made of, but on where it ends up in its planetary system's final architecture. And so we return to TRES 2b as our journey with this remarkable world approaches its natural conclusion, circling back to consider what remains unknown and what future might hold for our understanding. This darkest of planets continues its ancient orbit, unchanged by our distant attention. A world that exists independently of human knowledge, yet enriches that knowledge through its study. The mysteries that remain invite continued investigation, while what we have learned illuminates the extraordinary range of planetary possibilities that the universe contains. The extreme darkness of TRES 2b remains not fully explained despite years of study and modeling by scientists working to understand this distant world. Gaseous, sodium, potassium, titanium oxide, and vanadium oxide together approach the measured reflectivity, but do not quite achieve the less than 1% value observations reveal consistently. Something additional may contribute to the absorption, some chemical species or atmospheric process, not yet included in the models we have developed. Alternatively, the abundances or distributions of known absorbers may differ from model assumptions in ways that enhance their collective darkening effect. Future observations with increasingly powerful telescopes may resolve this mystery by detecting additional chemical signatures or refining abundance measurements for known species. The James Webb Space Telescope, operating at infrared wavelengths where many molecules have distinctive absorption features, represents a particularly promising instrument for atmospheric characterization of exoplanets. Whether TRES 2b will be prioritized for observation among thousands of known exoplanets remains to be determined by scientific committees balancing many competing targets. If observed, Webb could reveal details about atmospheric composition and temperature structure currently beyond our reach. The night side of the planet remains particularly mysterious, known only through indirect inference, rather than direct observation of its thermal emission and possible cloud features. Phase curve observations that track brightness throughout the orbit provide some information, but detailed mapping of night-side conditions requires sensitivity beyond current instruments. Future telescopes may achieve the precision needed to characterize the night-side temperature distribution, detect silicate clouds if they exist, and understand the full picture of atmospheric circulation. These observations would complete our understanding of how heat and material circulate around this locked world. The formation history of TRES 2b also contains uncertainties, particularly regarding when and how it migrated from its presumed formation location in the outer reaches of its original planetary disk. Did it migrate early, while the disk still existed, or later, through gravitational interactions with other planets no longer present in the system? Did any smaller planets exist interior to its current orbit before migration, and were they consumed or ejected during the giant's inward journey? These questions about the past inform our understanding of how planetary systems evolve and how common different outcomes might be. The host star itself will evolve over billions of years, eventually leaving the stable main sequence phase where it currently resides and expanding into a red giant. When this happens, the increased stellar radius will engulf the inner regions of the system, potentially including TRES 2b's orbit entirely within the expanded stellar envelope. Long before that final fate, increasing stellar luminosity will heat the planet further, changing conditions that have remained stable for billions of years. These changes lie so far in the future that they hold only academic interest, but they remind us that planetary systems are not permanent. For now, TRES 2b continues much as it has since reaching its current configuration eons ago, racing around its star every 2.5 days without rest. The day side faces its star perpetually, absorbing radiation and glowing faintly red from its extreme heat, darker than coal, yet visible by its own thermal emission. The night side remains in eternal shadow, warmed by atmospheric circulation, perhaps hosting exotic silicate clouds in its cooler regions where conditions allow condensation. The terminator ring separates these hemispheres in permanent twilight, winds flowing across it carrying heat from day to night continuously. 750 light-years away, in the constellation Draco, a faint star visible to dedicated observers on clear, dark nights, hosts this extraordinary world invisibly. The light we see from that star tonight left its surface around the year 1275 by Earth calendars, traveling through empty space for 7.5 centuries before reaching our eyes tonight. That light carries information about the star and its planet, encoded in brightness variations and spectral features that patient analysis can extract with appropriate instruments. Across that immense gulf of space and time, we have learned that the darkest planet ever discovered orbits there, coal black and glowing. The discovery of TRES 2b expanded our understanding of what planets can be, demonstrating that extreme light absorption is possible under the right conditions of temperature and atmospheric chemistry. Before this measurement, no one knew that planets could be darker than coal, darker than almost any natural substance, while still glowing visibly from internal heat. This single data point changed assumptions and prompted new modeling efforts to understand what combination of circumstances produces such remarkable properties. Science often advances through such unexpected observations that challenge existing frameworks and demand new explanations. More broadly, the study of hot Jupiters like TRES 2b has transformed our understanding of planetary system formation and evolution since the first such planets were discovered in the 1990s. These unexpected worlds forced recognition that migration is common, that giant planets can end up in places our solar system suggested they should not exist naturally. Thousands of hot Jupiters are now known, a whole population of scorched gas giants orbiting close to their stars throughout the galaxy in configurations once thought impossible. TRES 2b is one member of this population, distinguished by its extreme darkness but otherwise typical of its unusual class. Each exoplanet discovered adds to a growing catalogue that reveals the range of possibilities for worlds beyond our solar system throughout the galaxy we inhabit. Some are rocky like Earth, some gaseous like Jupiter, some icy like Neptune, and some fit no easy category from solar system experience at all. TRES 2b represents the extreme end of hot Jupiters, maximally absorbing, brightly glowing, tidally locked in the tightest possible configuration with its star. Understanding such extremes helps define the boundaries of what planets can become under different circumstances and environments. The universe continues hosting TRES 2b in its distant orbit, regardless of whether anyone observes or contemplates it from other locations across the cosmos. The planet needs no audience to continue its existence, orbiting as it has for billions of years and will for billions more under its star's steady illumination. Our awareness of it adds nothing to its reality, though it adds considerably to our own understanding of the cosmos we inhabit together. The knowledge that such a world exists, darker than coal yet glowing like embers, enriches the human picture of what the universe contains. And so the darkest planet ever found continues its endless journey around its star in the constellation Draco, 750 light-years from the eyes that have studied it. One hemisphere blazes under a star that never sets. The other rests in darkness that never lifts. And between them, winds carry heat in patterns established before any human ancestor walked upright on Earth. The atmosphere swallows light and emits heat. The orbit races onward, and the locked rotation holds steady, as it has for eons beyond counting. This world will outlast all human observers and all human civilizations, persisting in its ancient patterns long after the last telescope turns away to other subjects. The star will eventually change. The planet will eventually change. But on timescales so vast that current conditions might as well be eternal for any practical purpose. What exists now has existed for billions of years and will continue for billions more, a dark ember circling a distant sun. The cosmos contains wonders beyond easy imagination, and among them orbits this darkest of worlds, known to us now, continuing regardless, a small piece of a universe far larger and stranger than any single world can represent. The constellation Draco winds across the northern sky, the dragon of ancient mythology wrapped around the pole of our rotating world, in patterns recognized for millennia. Somewhere within that sprawling constellation, too faint to see without instruments, shines the star that hosts TRES 2b in its close embrace. The light arriving from that star tonight brings news of conditions 750 years in its past, a message traveling at the fastest speed the universe allows. What we learn from that light enriches our present understanding, connecting us to a world utterly unlike our own, yet governed by physics we share completely. The darkest planet ever found glows faintly red in the endless night of space, circling its star, locked in patterns that will persist for ages yet to come across the cosmos. Good night from the drowsy astronaut, and I'll see you again tomorrow.